Okay. So the day before, we did wholes and asymptotes. Okay. Both vertical and horizontal asymptotes. So let's talk about the breaks in continuity. Okay. That means what x can't be. There are two kinds of breaks. One of it is called a removable, aka a removable is also called what? A removable is also called a what? A removable is also called what? Vertical asymptote is not removable. How about that? So if it says removable, aka what is that? Removable and non-removable are both discontinuity. That means what x can't be. But if I want to use the word removable, discontinuity, what's another name that's a lot shorter than say removable? Read that really quickly and tell me. Removable discontinuity is, it's a what, Brandon?
It's a hole.
It's a hole. Okay. Okay, it's a hole on the graph. Non-removable discontinuity. It's called a what? What kind? Yes, it's called a vertical asymptote. So you guys need to know those words. Sometimes they use whole, sometimes they use vertical asymptote, sometimes they use removable, sometimes they use non-removable. Okay. Then we went on and talked about and introduced you guys horizontal asymptotes. Okay. There are three cases. When do you not have a horizontal asymptote? Beautiful. When the numerator degree is bigger than the denominator. Beautiful. When do you have a horizontal asymptote at y equals to 0? That's right. That's case number 2. Well, obviously that will leave you the last case. What's the last case? When they're equal. If the numerator degree is equal to the denominator, what is the horizontal asymptote? Y equals to what? And what is A over B? Do you guys agree? All right. So we did a few examples. So let's remind ourselves very quickly again with these examples. What do we do to find the restriction of the domain? You said what equals 0? What do we do? Yeah, what do you do? What is it? Factor. Once you're done factoring, what do you do next? That's right. Only the denominator needs to set equal to 0. Okay, so we did 1 and 2. We're going to continue with 3. Ready? Same instruction. Determine restrictions on the domain. So tell me, Brandon C., how do we start determining the restriction of our domain?
The numerator is bigger than the denominator.
That's horizontal asymptote. How do we decide what domain cannot be or can be? MIH. We do. But before we do anything, what do we do? Factor. Can the top be factorable? Yeah, okay. Let's factor the top. Why don't you take a minute and factor the top with your partner? The bottom looks like that's as far as you're going to go. But the top can go a little bit further. So go ahead and factor it out, and then I'm going to shuffle the card and call you. Talk to one another, guys. Okay. Ainsley, did you come up with the two factors on the top, hon?
On top, I got 2x minus 5 and 6 plus 2.
2x minus 5 and x plus 2. Someone confirm that for me? Perfect. Okay. So right away, we are going to take the denominator and we do what? Add equal to 0. All right, here's the denominator. We're going to set equal to 0. Lena, can you help me solve for x? Can you tell us what to do? Good job. Okay, so x equals 5 over 2. So we're going to write domain. Thank you. All real numbers, not including what? 5 or 2. Gorgeous. Just like you guys. Okay. Now, that's answering the first part of the instruction. State the restriction of your domain. Next, it says we have one restriction. So it said, do they, or in this case, does it represent a removable or non-removable? What does it represent?
Removable.
How do you know?
Because 2x minus 5 does not belong there.
That's what x can't be. How do we decide what's removable? What makes that value removable? What must be true?
If the factor x minus a can be removed, you can't.
Oh, if it can be canceled, right? Cancel means getting rid of it. Getting rid of it means I can remove it. Would you guys all agree with that? Can I cancel that factor?
Yeah.
Yeah, look at that. Gone and gone. What's left over? X plus 2, guys, is the simplest of that fraction. So we're going to answer this question. Removable discontinuity at where? Yep, x equal to 5 or 2. Can you see the difference between how we wrote the domain and the removable? The removable is equal to, okay, but the domain is what's not equal to. Brandon?
Whenever there's giant words, we write whole.
Yes, you can totally write whole at. Okay? But if I spell out removable, then you also need to know whole is the same. Okay. Next, we answer that piece. Do we have any non-removable?
No.
No, there's no more discontinuity. How many discontinuity do we have?
No.
Uno, and it's all removable. The rest of them are not discontinuity. Okay? Now, next, it says, is there a horizontal asymptote? How do we decide now to see if it's a horizontal asymptote or not? Okay, degree. What's the degree on the top? 2. What's the degree on the bottom?
1.
What happens when the degree on the top is bigger? No, HA, because the degree on top is bigger. And that's that example. Now we're going to go on to 2 more, or I think 3 more, and we'll call it a day. Example 4. Can you help me read the instruction to example 4, please, Hope?
Write a rational function with the following requirements. A removable discontinuity at x equals 1.
Good job. Okay. A rational function. Is that a function that has fractions or no fractions? It has fractions. Very good. Okay. So I'm going to start with a fraction bar. What does it mean to have a removable discontinuity?
You can be canceled.
I can cancel. Okay. What do we do x equals -4? How do we get that value? How do we go backwards? What do we put in the equation? X plus 4. Okay. Remember, discontinuity is what the bottom can't be. So I'm going to start with x minus, guys. It's always x minus. And then your x value is -4. That's how some of us know right away is x plus 4. What's on the top? Also has to be what, Gemma? You guys agree with that statement? Okay. On the top also. Remember, it's always x minus, okay? Just like x minus h, and your h value happened to be that, okay? Now, right now, can I reduce those? Yeah, that's why it's called a what? A removable. So did we right now meet the requirement of a removable at x equals to -4? Yeah, so all we gotta do is simplify that. R of x equals x plus 4 divided by x plus 4. That's all they wanted. Look at that. Now, technically, class, you can add a lot of stuff to this, okay? So all of us can technically have different answers and still be right, as long as that requirement is met. Okay? Number 5. Can you help me read number 5, please? Brandon N. Good job. So what did we start out with? Fractions or non-fraction? Fraction. Okay, so we're going to start out with a fraction bar. What does it mean to have a non-removable at x equals to 8? Is that on the top? Is that on the bottom? Let's decide location. All bottom. Okay, all discontinuity is on the bottom. What did we start out with? X plus or x minus? X minus. What's our value here? 8. Okay. If it's a non-removable, does the top have to have the same thing? No. Okay, so I have met that piece. The next piece that we have to meet is this. A horizontal asymptote at y equals to? When would you have a horizontal, oh, well, I can't speak. When would you have a horizontal asymptote? That's not 0. What must be true based on your notes? Degree on top must be the same as degree on the bottom, on denominator. Okay. Right now, what's the degree in the bottom? 1. For us to have a degree in the top to be the same, what would you have?
Anything that has a degree of 1.
Anything. What would you want that anything to be? 2x seems beautiful. But why 2x, Emma H?
Because in order to get the horizontal asymptote to be 2, the A over B has to be 2 or 1.
Ah, okay. I'm going to write x first. By the way, can I write x minus 100? Can I write x plus 1,000? Can I write x anything? Or just x? Okay. But just like Emma said, she said, right now, if she doesn't have a 2 next to the x, what is your HA? 1. Because the top has a leading coefficient of what? 1. The bottom has a leading coefficient of what? 1 divided by 1 is? 1. But your restriction said, I need a horizontal at 2. That means on the top, you need to have a leading coefficient of 2. So now if we check, on the top is a 2, on the bottom is a 1, 2 divided by 1 is 2. So that meets that requirement. And box that up. Okay. Brooke, can you read number 6 for us, please?
A whole at x equals 3, a vertical asymptote at x equals -5, and a horizontal asymptote at y equals 0.
There's a lot going on here. What do we start out with? Emma H, what do you want to start out with?
A fraction.
A fraction is right. Okay. A whole, that means what? Removable or non-removable? That means the top and the bottom should be exactly the same. All right. We're going to start out x plus or x minus? X minus. X minus what? 3. Beautiful. Check that piece. A vertical asymptote. Is that a removable or non-removable? What? Non-removable. Remember, a whole is removable. Vertical asymptote. This is non. Sorry, this is whole is removable. And a vertical asymptote is a non-removable. Okay. If it's a non-removable, where would you put it? Both top and bottom or just one place? Bottom only. We're going to start with x minus, x plus. X minus a what? -5. Okay. So now, we're going to move on to the next one. I'm interested in a horizontal asymptote of y equals to 0. How do we get a horizontal asymptote of y equals to 0? What must be true?
The numerator degree has to be bigger than the denominator.
Degree is bigger on top. Are you sure it's bigger on the top?
Has to be smaller.
Oh, it has to be smaller. So that means the bottom is bigger. Would you guys agree with that?
Yeah.
Degree is smaller on top. Okay. So the top degree has to be smaller than the bottom degree. Okay. So let's check our degree really quickly before we proceed. What's the degree on the top? 1. What's the degree on the bottom? 2. Does that meet the requirement?
Yeah.
We're good. We don't have to add any more. You can, but you don't have to. So right now we're going to FOIL it out and that. Okay. So foiling, x minus 3 on the top is beautiful the way it is. X minus 3 times x plus 5. We're going to FOIL the bottom. X minus 3 all over. X times x is x squared. Negative 3 times x is minus 3x. And then plus 5x. And what's the n? Minus what? 15. Okay. Then let's combine. And then we're just going to box this up. On the top, we still have an x minus 3. On the bottom, x squared. Plus how many x's? 2. And then minus 15. And that, my dear, is that rational asymptote that matches all of the requirement. And guess what? That is an egg roll.